Here we introduce WaLTER, the wheel and leg tumbling expedition robot. WaLTER is a novel quadruped morphology that seeks to capitalize on the many benefits of hybridizing wheeled and legged robots. Existing morphologies like Animal or the Go2W add wheels to typical quadruped designs in an effort to increase longevity. Other hybrids like WEGS or Alpha WaLTER modify the circular wheel design by introducing geometric interferences that help with climbing obstacles. WaLTER's design combines and expands on these hybrid approaches with the inclusion of a continuously rotating distal linkage, two wheeled contact points per leg, and a torsionally compliant waist joint that separates the front and rear body segments. WaLTER's continuous knee rotation and shin geometry allow for a tumbling gait that discretely changes contact patches without the need for a swing phase. This tumbling motion is further enhanced by the rotation and deformation of the wheels as they grab onto new surfaces. The continuous knee rotation is also useful for establishing new contact patches on soft terrain when the wheels sink down and get stuck. To further evaluate the effectiveness of WaLTER's leg morphology, we compared its tumbling gait to a hypothetical big wheel model, which replaces the distal linkages with large wheels of the same diameter. Both models were tested using feed-forward control inputs across a series of progressively increasing obstacle heights. In this test, WaLTER significantly outperformed big wheel, scaling ledges up to 40% taller. The compliant waist joint allows the front and rear legs of the robot to adjust to out-of-plane disturbances. To illustrate the utility of this joint, two simulations were created. On the left, the waist joint is locked and the robot rolls over while trying to descend the ledge. On the right, the waist joint is free to rotate, allowing the front legs of the robot to passively adjust to the new surface and prevent the rollover. WaLTER has a total of 16 actuated joints, so to control our prototype, we devised an intuitive control scheme that collapses down this action space to be used on a standard gamepad. The left joystick controls the wheels, the right joystick controls the knees, and the buttons can be used to select predefined configurations that assist in turning, climbing, and other tasks. With this teleoperation scheme, we demonstrate the physical prototype's ability to traverse many types of obstacles. Teleoperators are able to reliably travel up and down a set of scaled stairs and across various piles of unstructured rubble with only a few minutes of training. In addition to the teleoperation scheme, we propose the use of deep reinforcement learning to develop more intelligent control policies that will eventually adapt to the terrain while obeying a user's commanded input. To analyze efficiency, the power consumption of the robot was monitored over a selection of different terrains and locomotion modes. These experiments suggest that wheeled locomotion on flat terrain was the most efficient mode of travel, yielding a predicted range of 4 kilometers. In the future, we hope to create a human-scaled prototype that can assist in real-world scenarios like search and rescue missions or explosive ordnance disposal.